just to kind of compare, traditional units to linear units and whatnot. So we've got a desktop simulator similar to RODSTAR, SROD, something like that, that does predictive evaluation. It's also built into the drive, so it can run in real time as the well is running. So it's doing predictive data versus actual data all, at the same time, which is kind of a useful tool. So we just picked kind of an example here. Let's see, we picked a class 1 geometry pump jack with a 96-inch stroke, 5,000 foot deep well, 1.5-inch pump at 10 strokes per minute. Ran the simulation, and we did side-by-side comparisons. And so here's the velocity profile out of the simulation. This is rod velocity, polished rod velocity, and time on the x-axis. And this kind of pink color, we've got the conventional pump jack. You can see this sort of pseudo-sinusoidal, or the 4-bar linkage, sort of that usual velocity profile you get with one of those types of units. And on the linear unit in blue, typically we're looking at more of a trapezoidal velocity profile. And here I picked acceleration rate, 75% acceleration up to max speed, which I matched the conventional unit as closely as I could, right? So the peak velocities were the same anyway. And I kind of matched the accelerations to sort of average what that looks like. And so we're running the same average strokes per minute, same barrels per day, same stroke length, or approximately, very closely the same. So now let's look what we can do to make some improvements to that motion profile. And as I said earlier, one thing we can do is we could modulate the acceleration rate. So we could accelerate harder and decelerate harder into the turn. So now this is the upstroke here, right? Positive velocity in the upstroke. Here's the downstroke portion of the cycle. So this represents one cycle of the pump jack, right? So if we accelerate harder and go up to a slower maximum speed, we can get the same average strokes per minute, same stroke length, and we can limit the peak speed. There's been many papers written on rod fall velocity, right? Maximum rod fall velocities for solving rod buckling issues and whatnot. So we can immediately reduce that maximum rod load velocity. And you might ask, well, what effect does that have accelerating harder like that? What adverse effect might that have on rod dynamics and whatnot? Well, we'll get into that a little bit. The other option would be by accelerating harder. If we wanted to maintain the same constraint on peak velocity, we accelerate harder up to that peak velocity and down, same on the downstroke. And by doing that, we would actually increase the stroke length, right? So with the same peak speed, we could run a longer stroke length and get more production rate. I think, let's see, that would be illustrated down here, right? So we went from 212 barrels per day up to 309, 145% increase in production. So we can lower peak speeds, we can quickly change direction. By accelerating harder, we can reduce the speed in the straightaways. We can cover a greater distance and increase the stroke rate without exceeding rod velocity fall limit. And let's get a little more detail into this now, exactly how we go about doing this. What makes it easy to do a lot of this velocity manipulation is the fact that we have a very low inertia system.